Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Power. As always, please watch this video as an active learner. Time considerations aren't involved directly in the definition of work. You can lift a barbell weighing 400 newtons through a vertical distance of a half a meter, and that's 200 joules of work, whether you do it in 1 second, an hour, or a year. But often we worry about the time it takes to do some work, and that's when we start talking about power. Power is a scalar quantity, and we define average power as follows. The definition of average power, subaverage, is defined this way. When a quantity of work delta W is done during a time interval delta T, the average power P sub average, or work per unit time, is defined by P sub average equal delta W over delta T. The unit for work is a watt, W-A-T, abbreviated capital W, where 1 watt is defined as 1 joule per second. So a watt is a joule per second. Some notes. Again, the average power is not a vector, but it can be positive, negative, or zero. And power is not the same as energy. The two cannot be interchanged. Power units can be defined to define new units of energy or work. For example, energy companies often talk about the kilowatt hour, kWh, and that's the commercial unit of electrical energy. So 1 kilowatt hour is a kilowatt, and a watt was a joule per second, so we have that here. But if we multiply that by an hour, which is 3,600 seconds, the seconds cancel, and you end up with this number. And so 1 kilowatt hour is a unit of energy or work, and it's 3.6 megajoules. So a kilowatt hour is a unit of work or energy, not power. When a force acts on a moving object, it does work on the object unless the force and the displacement are perpendicular. We've studied that before. The corresponding power can be represented in terms of force and velocity. And you think about the units, and that makes sense. Suppose that a force, F, this is the vector, acts on an object while it undergoes a displacement of delta S, and this is the delta S direction. Now, if F parallel, that's what that little double bar means, is the component of F tangent to the path, that means parallel to the direction of S, then the work, delta W, is F parallel times delta S. And again, those two directions are the same. So then that means that the average power is, this is going to be the delta work divided by delta T. And so that means that this, I can rearrange this taking delta S over delta T. So that really is the force parallel times the average velocity. There are some problems where this is a very useful characterization. Make sure you understand that that's the force parallel, though, so there may be some trig involved. Now you might say, well, what is a horsepower? Well, a horsepower is also a unit of power, but a horsepower is a unit of power in the British system, not the SI system. 1 horsepower is equal to 550 foot-pounds per second, and if you were to change that to minutes, you would get 33,000 foot-pounds per minute. That means that a horse, in this theory anyway, would do 33,000 foot-pounds of work every minute. A useful conversion that often comes up is changing horsepowers to watts, and 1 horsepower equals 746 watts, or if you express it in kilowatts, 0.746 kilowatts. Let's do a problem to exercise our abilities with these equations. So suppose a jet airline engine develops a thrust, a forward force on the plane of 15,000 newtons. When the plane is flying, and that 15,000 newtons is roughly 3,000 pounds. Now you need to know that for the second part of the problem. When the plane is flying at 300 meters per second, and that is approximately 670 miles per hour, the question could be, what horsepower does the engine develop? This is a dimensional analysis problem as well as a power problem. You know what to do. Let's see how you did. Okay, so the power is F times V. So this is newtons times meters per second, and that gives you watts. But then we have to change the watts into horsepower for this problem. So this is the wattage that we found times 1 horsepower per 746 watts, and that gives us 6030 horsepower. Here's another problem for you to consider. In this problem, a runner must overcome the increasing gravitational potential energy as she climbs the stairs of a tall building. These things happen at the Hancock Building and perhaps the Sears Tower. The rate at which she does this is directly related to the average power output. As part of a charity fundraising event, a Chicago marathon runner with mass 50 kilograms runs up the stairs to the top of the Willis Tower. Actually, it's not called the Sears Tower anymore. It's called the Willis Tower. The tallest building in Chicago. This is how tall it is. 443 meters in 15 minutes. That's moving pretty fast. What is her average power input in watts, in kilowatts, and in horsepower? So there's several answers here. You know what to do. Let's see how you did. Okay, well, the amount of gravitational potential energy that she did is she did mgh. So this was her mass, that's the acceleration due to gravity, and this is how many meters she went up. So it's that many joules when you multiply it all together. Now that took 15 minutes, which is the same thing as 900 seconds. And so you would take the work divided by the time, and you would get watts. So this is the answer in watts. This is the answer in kilowatts, and if you change it to horsepower, you should check this, but you get this answer. Let's look at another problem, and this is powering down because we're almost finished with this chapter, but we end up powering down with a concept question. A baseball is dropped from a tall building. Which of the following statements is true, regardless of the power delivered to the baseball by the gravitational force? Power is constant in time as the ball falls. The power decreases in time as the ball falls. The power increases in time as the ball falls. You know what to do. Let's see how you did. Since power can be written as power is equal to F times V, the correct answer must be C, because certainly the velocity increases as it goes down. The gravitational force remains constant, but the speed increases with the free fall equation. And so if it increases, it can't be constant or decrease. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.